Start your day with a smile because you are lucky to have seen a new day. Good morning to one and all present here. Good morning is not just a greeting, it signifies a hope that a beautiful morning will bring a smile on your face and happiness in your life. On behalf of PG and Research Department of Mathematics, DG Vaishnav College, I welcome all the CSIR aspirants. Prayer is talking to God Almighty, the creator of whole universe. So let's begin our session with the presence of God. Now Tamathai Vatu followed by college prayer.
நீராறும் கடலொடுத்த நிலமடந்து கெழிலொழுகும் சீராரும் வதனமென திகழ்வரத கண்டமிலே எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் மிகுந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
योनिं निहितं च सत्ये सत्यस्य सत्यं ऋतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिः सतां दर्शनेस्तु भवत्तनूनाम् नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनाम विभेदेन जगत्क्रीडति यो यतः ॐ शान्ति शान्ति शान्तिः.
This is C4 workshop, chase, which will make the CSIR aspirants to go to the next level. Today, our research person is Dr. R. Sivaraman, Associate Professor, PG and Research Department of Mathematics, DG Vaishnav College, Chennai. Now, I hand over the session to you, sir.
So, good morning to all. The screen visible, sir? Hello?
Yes, sir. Yes, sir.
Visible?
Yes, sir.
Okay, so good morning to everyone. I'm happy to present today's program for C4 conducted by DG VAISHNAV College. As you know, this is a very noble objective, especially for students aspiring to write a CSAR NET exam in the upcoming months. We have completed 14 sessions as far as I know. This is the 15th session that we are going to begin today. So before we start formally, I used to just any session or any class. Usually, I start with properties of numbers. Being 15th session and today's date is 31. You know, 2 power 4 minus 1 is 15, and 31 is 2 power 5 minus 1. So these two numbers, 15 and 31, are powers of 2 minus 1. In fact, they're consecutive powers of 2 minus 1. And such numbers are called Mersenne numbers. Numbers of the form 2 power n minus 1 are called Mersenne numbers. Especially if the number of the form 2 power n minus 1 is a prime number, it's called a Mersenne prime. So 31 is one of the Mersenne primes. And I observed that if you add consecutive powers of 2 beginning from 2 power 0, that is 1 plus 2 plus 2 square plus 2 cube plus 2 power 4. If you add up to 2 power 4, you get 2 power 5 minus 1, which is 31. So it is so intimately connected. And with this short introduction of date and other things, I will begin my session formally. So a sequence is defined as a, of course, I am talking about sequence of real numbers. So sequence of real numbers Sn is defined as a function from set of natural numbers to set of real numbers. So the domain is set of natural numbers, codomain is set of real numbers. Whereas if you consider sequence of complex numbers, the domain is n, or even integers. Sometimes you may even take integers as domain for complex number. And of course, the codomain is set of complex numbers. So this is how, so any sequence is basically a function. Okay, so but we fix the domain and codomain accordingly. So sequence itself is a function. Now, I'm going to give some examples of problem that you usually get and bit understanding of the concepts of all types of ideas available in sequences. Particularly, the first few slides will be regarding the ideas and the things that you have learned in your colleges at all levels, like UG third year as well as in PG. So I'm going to present most of them in visual manner because a picture is worth 1,000 words. And therefore, keeping that in mind, rather than solving problems after problems, which I have been doing in the previous classes, nearly I have solved 50 problems in the previous 2 sessions that I have taken. Today, I will solve the problem as well as show the concepts visually. So that's the other thing that I want to do today. And I hope you will get benefited out of this. So if you consider the sequence recursively defined like xn plus 1 is cos of xn, this is the recursive sequence. The sequences are in two types. The nth term of the sequence may be defined explicitly in a simple function form like xn is 1 by n square, xn is n plus 1 by n, or xn is something like sine pi by 2n. So these expressions are explicitly defined as a function of n. And you can plug in n, 1, 2, 3, so forth because the domain is set of natural numbers. Now, we'll be considering mostly sequence of real numbers. I'm not going to take sequence of complex numbers in this presentation. The other category of sequence definition is through recursive way, as we have done here. So xn plus 1 is cos of xn. I'm defining the first term x0 as 1. So the x0 is initial term. So whenever you define a sequence through recursive way, you have to give an initial term. Only then, using that, I could generate the other terms, the subsequent terms. So if you define x0 as 1 and if you put n as 0 here, you get x1 is cos of x0 because n is 0 here. So x1 is cos of x0. x0 is defined to be 1. So x1 is cos 1. This 1 is in radian measure, not in degree measure. So if you take any calculator, scientific calculator, and plug in this value, cos of 1 radian, not degree, 1 radian, it turns out to be 0.5403. So this is the first term of a sequence. It is 0.54 is just less than 0.55. This is the plot of the sequence here. This first term, just 1 then 0.01 less than 0.55. So the first term is plotted here. This is my x1. Okay. And if you take the second term, you have to just substitute this value here to generate the next value. So x2 by definition is cos of x1. So just substitute here, you get cos of 0.5403. And again, if you take the calculator and put this value in the radian measure, 0.5403 for cosine value, you get 0.85755. It's just more than 0.85, so slightly higher than 0.85. So this is my first term, x1. This is my second term, x2. And if you compute the rest of the other values, which is plotted over here, for n is 3, you get x3, which is 0.65429. That is slightly more than 0.65 here. So this is third term, this is fourth term, this is fifth term, this is sixth term, this is seventh term, this is eighth term, ninth term, 10th term, and all you get. Now after some stage, you see the beautiful pattern here. Once after some stage here, if I continue plugging these values consecutively, you find that all the terms are grouping along a straight line. Initially the terms alternate, like first term is below this line and second term is above, then the third term is below, fourth term is above, fifth term is below, sixth term is above, but the gap is closing down. And after some stage, you find all the terms are grouping along this line, and this particular value that the terms are grouping out over here is basically defined to be the limit. In fact, if you look at the tabular column values, they all go very close to, say, approximately 0.73 or 74 or something, which is over here. So it's approximately, it is just slightly less than 0.75. So approximately 0.74 or something like that. Okay, 0.73 or 74 something. So this is going to be the limit, and this is the visual representation of seeing why that limit. And if you take the definition of limit of a sequence, for mod xn minus L is less than epsilon whenever n is greater than or equal to capital N. That capital N is a stage of convergence, and you see for the initial 5 terms or so, it is the answer that we get is not close to 0.73. But once you take terms beginning from 17th term or 18th term or near to 20th term or so, all the answers group along very, very close to the limit value. That is the significance of mentioning that capital N value. So the distance between the sequence terms of the given sequence and the limit that you call as L will be very, very small. After some stage, that stage is capital N. So that N probably here in this case in our example will be beginning from 17 or 18 or something. So for this particular sequence, okay, this is a geometric significance of observing a limit. The terms may oscillate, but after some stage it will align along a single value. It will converge to a single value. That convergent value is called the limit. Okay. And let me take the other sequence. Instead of cosine xn plus 1 is cos xn, I'm going to take sine xn. In this case, again beginning with x0 is 1, the initial term. x2 is this value. Again, this is in radian measured. Okay. So x2 is sine of 1, that is 0.84147. You see, this is the first term. This is 84147 is more than 0.8. So that is here. x2 sine x1 is 0.7452, that is less than 0.8. So that comes over here. This is, so if you plug in the other consecutive values, see up to 20 values, you probably may guess that the limit is 0.35 because it is coming very close to 0.35 up to 20 terms. You see, the 19th term is 0.35875. The 20th term is 0.3511. So this agrees to the 2 decimal places. But what happens is ultimately the sequence will converge to 0. So if you look at few terms here, you can't judge what could be the limit. It will deceive us. So this is why the definitions are so important. The significance of epsilon delta definition is very clearly depicted through this example, because you see, if you stop yourself at this number of terms, like as we did here, up to 20 terms, here it is very clear. It is aligning to a straight line along 20 terms. Up to 20 terms is very clear, and after that it is along straight line. But in this particular example, 20 terms are not enough, because up to 20 terms, maybe the terms are close to 0.35. But ultimately, if you go beyond 19,000, 20,000 or 50,000 terms or so, the answer is very, very close to 0. So this is why we require the stage of convergence. The significance of that capital N that we use in definition of limit of a sequence is because of this factor. See, up to this term, it will reduce to some particular value, but you may not guess that it is going to 0. But once you go beyond certain stage, that is why we write as the limit of the sequence is defined only when n tends to infinity, when n is very large, not like 20 or 30 or something. Okay, so you have to consider n very very large and see, even in that case, it is going to the prescribed limit value. If it is very close to that, then you say. So here it's a very classic example of getting deceived, because we often think that this will converge to 0.35, but actually the limit is actually 0 here, and that is clearly seen only after taking 19,000 or 20,000 or 40,000 or 50,000 terms. It is not very much clear at the beginning of the sequence. Some sequence may converge even after 1 lakh terms or 1 million terms. The initial 1,000 terms or 10,000 terms may not be seen to you that it is going to converge. In fact, it will increase rapidly and then drops down to a certain limit. So that is why the behavior of sequences are very random. I mean, there are many sequences which behave very chaotically, but after a certain stage, if the sequence is convergent, that is why the stage is important. So for this sequence in particular, I'm not bothered about the first 10,000 terms or first 5,000 terms, which may not convey any meaning to me and say any information that it is going to get converged to 0. But after 10,000 term or after 5,000 term, I'm primarily interested, because only those values convey the fact that it is going to get converged to 0. So this example says that, but for finitely many terms, you leave away. Even if they're not close to the limit value, you don't bother. But after that stage is what is prescribed by capital M. After that particular stage, your members of the sequence, the terms of the sequence, should be as close as possible to the limit value capital M. Of course, deciding what is L is a very tricky issue, especially for some trickier sequences and some complex sequences. But anyway, for small and easy to write sequence and easy to guess sequences, it is quite easy to determine what is L, the limit value. But there are some tests which tells you whether the sequence converge or not, but it doesn't give any information about the limit value. You have to know some other techniques to determine it. Now, this is a very classical sequence which I like most. This type of sequences you may not have seen in your curriculum. Xn plus 1 is 4 times Xn times 1 minus Xn. I define the first term x1 as 0.3. So the first term x1 is 0.3. You see here. Where is the first term? I have defined x1 as 0.3, but I have plotted only x2. x2, if you do that here, you get 0.84. This is second term. x2 is 0.84 and x3 is 0.5376, which is just less than. So you have to just substitute here. If you substitute 0.3 here, you get 4 times 0.3 times 1 minus 0.3. 4 times 0.3 is 1.2. 1.2 times 0.7 is 0.84, the second term. And then if you substitute 0.84 here, you get the next term, 0.5376. And if you substitute 0.5376 here, you get the next term, 0.994345. And if you keep on doing this, you see the terms alternate, like one coming up, one coming down, then it's going up, then it's coming down, then it's going up, then coming down, and it's very randomly behaving, not like this. Okay, but again, you could not deceive by first few terms. What happened to this particular sequence is that even if you count this for billion terms, the terms will behave only like this. Okay, it will behave only like this, but it will not exceed 1. So in other words, if all the members of the sequence are kept in a closed interval, like it starts at 0, it is all the terms of the sequence here in this case are between 0 and 1. You see, it will be above this line, x-axis, and it will not exceed 1 probably, because of this factors. This terms are less than 1, so they multiply together. Okay, so you see all the terms of the sequence are strictly less than 1. So any member of the sequence here is packed between, it is somewhere between 0 and 1, greater than 0 but less than 1. If you have such a situation where all the members of the sequence, terms of the sequence, are packed in a finite interval, like here in this case it's 0, 1, minimum value is 0, maximum value is 1. If it is packed inside that particular interval, like compact interval, then it is called a bounded sequence. So this is a bounded sequence, but it will not converge to any particular value. As you can see, there is no pattern that it is going to a particular answer like this. See here, it goes very close to 0. In the previous case, it goes very close to 0.73. All the terms align along a particular value. They come very close, but here the closest is not observed. If you take these three terms, the next term comes down, the next term goes up, then comes down, then goes up. So you can't find the particular alignment going to specific value. So there is no limit for this. In fact, this sequence is used in discrete logistic models and have a very significance in chaotic theory. There is a separate branch in mathematics called chaos, which actually involves so many things, and it is an important idea in a branch called population dynamics, where they use differential equations to study this kind of chaotic ideas. And even study of chaos is used to predict climate changes, weather predictions, and other things can be used. So this is a very important and significant sequence. Okay, the chaotic means not unclear pattern. I mean, you can't judge anything from it. Now, this is an illustration for saying sum of two convergent sequences is another, again, a convergent sequence. So I have two sequences, an is a increasing sequence, starts here, it increases and converges to this number, say capital A. So the limit of an is a. Bn is a constant sequence converging to b. Bn is constant sequence here. So if I add these two convergent sequences, just an example, okay, you can construct your own like this. If you add these two convergent sequences, I should expect a convergent sequence, another convergent, because there's a theorem saying that sum of two convergent sequences is another convergent sequence. So if you add two convergent sequences, you get another convergent sequence. Even this is true for convergent series also. Now listen. So this point is corresponding to an, this point is corresponding to bn. If you add these two, you get an plus bn. The first term in an is here, first term in bn is here. This is first term in a1, an plus bn. This is a1 plus b1. This is a2, this is b2. So this is a2 plus b2. Because the terms a2 are increasing, this height is also increasing. B terms remain, the sequence bn is a constant sequence. Okay, so because an increases, this also increases, the sum also increases. a3 b3, so this is a3 plus b3. a4 b4, so this is a4 plus b4. If this converges to a, this resulting sequence, namely an plus b, in terms of this sequence, converges to a plus b, which is sum of the actual limits. So the sum of limits is limit of sum. The sum of limits is limit of sum. So this picture clearly conveys that meaning, but for convenience, we have taken bn to be a constant sequence to show this particular alignment to you. Okay. Now, there may be two, you can give examples of two divergent sequences, but still there's some getting convergent. You can provide examples of two divergent sequences. That is, I can provide an as a divergent sequence, bn is also divergent, but still their sum is convergent. The example is this. So an is n is monotonically increasing sequences which is not bounded above. So this diverges to plus infinity, whereas bn is minus n is a monotonically decreasing sequence. So monotonically decreasing sequence which is not bounded below, therefore this diverges to minus infinity, but their sum converges, because if you add these two you get 0, that is a constant sequence, so the sum converges. So there may be some examples where not that always sum of two convergent sequences make the answer convergent. You may also give examples of two divergent sequences, but still their sum becoming convergent. So this is one thing that I want to tell you. But you can't probably give examples of sequences where one is convergent, the other one is divergent, but their sum is convergent. You can think about that. Okay, only if both the sequences are convergent, the sum is convergent. Okay, even if one diverges, the sum will diverge. Now, as I just told you in the example that we saw in the chaotic sequence here, this is logistic sequence. all the terms are between 0 and 1. Every term of the sequence is packed in the interval between 0 and 1. Okay, similar to that, the bounded sequence is a sequence for which it lies between two particular values. So here it is between small k and plus k, capital K. So if all the members of the sequence or all the terms of the sequence are packed between two particular finite values, then the sequence is called a bounded sequence. So here the terms of the sequence are packed between small k to capital K, and therefore this is an example for bounded sequence. And this particular sequence tells you if a sequence is monotonically, if it's non-decreasing, then it converges to its least upper bound value. So this is a non-decreasing sequence, it converges to this particular number. Here it's going very close to 0. So 0 is the least upper bound. And this another case, a monotonically decreasing sequence converges to its lower bound. In fact, this is GLB. Okay, so but this convergence is not seen immediately. Only after some stage the members of the sequence will go very close to this. So this capital N, the stage of convergence, is very, very important. This capital N is actually called the stage of convergence. You may not see the fact that all the terms beginning from the first term will be close to this GLB value. Only after certain stage here the members of the decreasing sequence will be close to the limit value. In fact, for a decreasing sequence, if it monotonically decreasing sequence which is bounded below by its GLB, the limit is its GLB. Similarly, if the sequence is monotonically increasing and if it is bounded above, then it will converge to its LAB value. So it will get very close to that number. But this is a case where there is an upper bound here. The upper bound is capital K, but there's no lower bound. The terms goes very close. Of course, for this terms, all the terms are below plus K, capital K, but there's no lower bound. I mean, the terms here goes up to minus infinity, decreases rapidly. There's no lower bound, so therefore this cannot get converged. Okay, so if you take one term, it is going up above the x-axis, other term going below x-axis. The next term goes above x-axis. The next term also go above x-axis, but the next term goes below x-axis, and then it is further decreasing. So it's an oscillating sequence here. In fact, it's an infinite oscillating sequence. Okay. Whereas if you take minus 1 power n, which is minus 1 plus 1 minus 1 plus 1, that is an oscillating sequence, bounded sequence, but it is a finite oscillating sequence because all the terms are between minus 1 to plus 1, which is a finite interval. Okay. Now this is a classic proof that you could have studied in your class, showing that every convergent sequence is bounded. So if Sn is a convergent sequence, then Sn is bounded. This part you could have studied in your textbooks, in your class. The proof goes this way. See, as I told you, the members of the terms of the sequence start here. It will come here, it will come here. So this is my limit L. This is my limit L. So the terms of the sequence goes very close to this limit value only after this stage, capital N. So once I come to this stage, see, beyond this stage, it may go outside this or outside this. You see, these terms are outside the strip. L minus capital L minus small l, capital L minus small l. So this strip L minus L to L plus L is a strip collecting terms which are very, very close to the limit value L. But if you want to collect those terms, it may not happen immediately, because you see in this case, this terms are outside the strip, and this terms in fact less than the values of the strip, and this values are greater than the values of the strip. So only if you consider this stage, capital N, the terms of the sequence are squeezed in between L minus L to L plus L. So it is very close to capital L. So in that case, you know, the terms of the sequence, which are infinitely many, from N and after N, is between small L minus L to L plus L, capital L minus small l and capital L to plus L. But what happened before that? Before that, up to N minus 1 term, if N is less than N, up to this stage, you take maximum value, which I call as capital M. So beginning from here up to this, before this blue term here, all the terms are less than the maximum number. So if you now take Sn for all these terms up before capital N will be less than capital M, because this is the maximum among the previous values. And from N, it is always between this strip L minus L to L plus L. And therefore, I can write Sn as less than this M, which is maximum before capital N, the stage of convergence. And then I can write Sn is less than capital M plus L minus modulus of L, capital L plus L. So it is between these two strips. It is not going beyond this. So this is that strip. So this bound will take care of all the terms from capital N and rest of the terms. M will take care of all the terms of the sequence before capital N, the stage of convergence. So in all, you see the whole terms of the sequence is between this line and this line. So any convergence sequence is in fact is bounded. This is how the proof goes actually. If you look at the proof of convergence sequence, this is how it goes. So you consider for the first n minus 1 terms, capital N minus 1 terms, you consider the maximum and call it as capital M. So mod Sn is less than M for n1 to n minus 1, which means up to this stage, all the terms of the sequence are less than this maximum number. And after that stage, it is between these two strips. And therefore, if you can write Sn less than M for the first n minus 1 terms. For the rest of the terms, you can write small l plus modulus of capital L. So Sn is less than some finite number, which means that all the members of the sequence or terms of the sequence is packed between two finite values. Therefore, the sequence is bounded. But converse is not true. As I told you, bounded sequences may not be convergent. As a classic and very simple examples, minus 1 power n. Okay, minus 1 power n is a bounded sequence, but it is not convergent. It is oscillating sequence. But it will have a convergent subsequence. Okay, though the sequence is not convergent as it is, any bounded sequence might have a convergent subsequence. Okay. Now you see this, all the terms of the sequence are packed between these two terms, these two lines. It will not exceed beyond that. But when you increase the number of terms, the values of n, you see the successive differences. The difference between a particular term and the next term keeps on decreasing. That is why this oscillation goes down. The big oscillation here is come down here and then come down. The oscillation height of the oscillation goes to 0, which means all the terms get converged to some number, some limit number here. So this is a bounded sequence which converges. Whereas this is a bounded sequence which does not converge, because you see the oscillation remains same. It's not closing down like this. If the height of the oscillation goes to 0 after some term, here this is bounded because all the terms of the sequence are between these two numbers. So it is not going beyond that. So as I told you, if the members of the sequence are packed between two boundary lines like this, the two red lines here, dotted lines, then it is a bounded sequence. So the sequence is clearly bounded, but what happens is the height of the oscillation doesn't decrease. It is not going to 0, as we saw here in this first example. If you write this height has decreased like this, and that is decreased to this, that is decreased to this. So the height of the oscillation of the terms of the sequences as n increases will go to 0, which means the terms get convergent. So this is a bounded convergent sequence, but this is a bounded sequence which is not convergent. This is what has happened. A similar thing happened to minus 1 power n, because if we take minus 1 power n, the odd terms remain at minus 1, the even terms remain at plus 1. So if you take the height of the oscillation, it remains 2 always, because the difference between 1 and minus 1 is always 2. It remains constant. It will not decrease. Okay. So this is one such example. And coming to the next concept called Cauchy sequence. Cauchy sequence is a sequence where you don't have the idea of the limit value, but what you can see is this example is a Cauchy sequence. Here you see the terms of the sequence initially are having very much difference here. The difference between these two terms is somewhat larger, but difference between here, this particular terms are smaller, successive terms are very, very small. You can't even see here, it's very small. So I don't know what could be the limit, but it will if the height of the oscillation goes to 0, which means the height will go to 0 only if the successive terms or the terms in the particular neighborhood are very, very close to each other. Only then the height will go to 0. Like here it is not so, because you see the height is always same. So the difference between successive terms, difference between this term and this term, this term and this term, remains always constant. Like the difference between 1 and -1 with respect to the sequence minus 1 power n. Then that is why those sequences are bounded, but they are not Cauchy sequence, because the difference is not less than a particular number. It is not going to 0, the height of the oscillation. If the height of the oscillation remains constant, then such sequences will be bounded, but they will not be Cauchy sequence. So this is an example. So this is Sn, this is S, the limit of the sequence Sn. So you see, after some stage, before n, the terms may be outside this limit value. The difference between Sn and S is quite large. It's not very close to S. But this strip here is modulus of Sn minus S. The difference between Sn and S. Okay. So that is coming to this inside the strip. The values of differences of Sn and S come only after this stage. This particular strip comes only after n greater than or equal to capital N. So beyond capital N, Sn, the terms of the sequence Sn is very, very close to S. You can see, so it converges to S. And you can see the sequence is this difference is more than this difference. So the difference between these two terms is less than difference between these two terms. Similarly, the difference between these two terms is less than difference between these two terms. The difference between these two terms is less than or equal to difference between these two terms. So as you increase small n value, if you go beyond certain term, the difference between the terms, the members of the sequence is very, very small. Only then it will get converged. Okay. Now within epsilon distance, this is Cauchy sequence. I may not bother if I do not have the knowledge of the limit value. Yes, then what I am going to do is I may take two arbitrary terms Sm and Sn, two general terms. So if I choose Mn greater than or equal to capital N, and if the difference between Sm and Sn lies in this strip, so this values are values which gives you the condition that modulus of Sm minus Sn or Sn minus Sm, whatever it is less than epsilon. So this is epsilon strip. So here it is greater than epsilon, so they go beyond the strip. Any values here, the black dots lying inside the strip will satisfy Sn minus Sm less. That is, difference between Sn and Sm is less than epsilon. So here I do not have any idea about what the terms are going to, where the terms are going to. I do not have any knowledge about the limit, but I can specifically say that it is going to get convergent to some value, because of course for sequences of real numbers, Cauchy sequences, there's no difference between convergent sequence and Cauchy sequence. Every convergent sequence is a Cauchy sequence, and every Cauchy sequence is a convergent sequence. In general, with respect to Euclidean space R power n, there's no difference between convergent sequence and Cauchy sequence, like for a whole Euclidean space. But there are some spaces, general metric spaces, for which in any metric space, of course, convergent sequence will be a Cauchy sequence, but not all Cauchy sequences are convergent. You can give plenty of examples for such thing. In particular, if you don't take whole space but take a subspace like open interval 0, 1, then I can define a sequence like 1 by n for n greater than or equal to 2. That 1 by n converges to 0. 1 by n is a Cauchy sequence in the open interval 0, 1, but it converges to 0, which is not in the space, because the space is open interval 0, 1, and 0 is not in the set. So it converges to a value which is not in the set. So not all Cauchy sequences are convergent, but any convergent sequence is a Cauchy sequence. But with respect to sequence of real numbers, if you take whole real numbers, there is no difference between convergent sequence and Cauchy sequence. They remain one and same. They behave in the same way. There's absolutely no difference between them. Okay. So this pictures will give you an actual idea about what we are doing. See, we always study through definitions and theorems, but we hardly could see what is happening behind what we write. So that is the point that is to be conveyed in this topic now. So this is stage of convergence, which means here the distance between Sn and the limit value is less than epsilon. So this strip gives less than epsilon condition. This is more than epsilon. So I may not expect the terms to be very close right from the initial term, but after some stage they will be very close to each other. That stage is capital N. So N is actually the stage of convergence. Okay. So those who are interested, so I may possibly give some more information than what I have done here. If you're interested, you can keep notes with you and write them, whatever I say. Those students who are very much interested, because these are main important basic things that you need to know probably when you prepare for CSIR or set exam or something, because these basic things are very essential to tackle difficult problems. Okay. Then we probably see the next concept called limit superior and limit inferior, or infimum supremum, whatever it is. Now if you take this for each term here, listen, supremum is the largest value, infimum comes to the smallest. So for this particular portion, this is a supremum. For this portion, this is a supremum. This is the infimum for this portion. So if I take this portion of the graph, the largest part comes here. So this is supremum of those terms, and this is infimum of these terms. So supremum comes above and infimum comes below. So like what you can see, view supremum and infimum as if these are the, if you can think as a room, supremum always align like ceiling of the room, so in top portion, and infimum values align in the floor, the ground portion. So this is supremum values in the above portion, top portion, and infimum will align in the bottom portion. Now this is supremum up to certain term, this is supremum up to next few terms, this is supremum up to next few terms. If you now take limit of this supremum, that is limit supremum. So this is supremum for few terms, this is supremum of next few terms, this is supremum for next few terms, and all those things. So this is supremum of collection of few terms, and you see this supremum value sometimes may converge. If it converges, then you call that as limit supremum. So the set of supremums may also converge, and that if it is convergent to certain number, here in this example the supremum is converging to 1, so limit supremum is 1. And similarly the infimum may start here, it is very close to less than minus 1.5. So infimum of this portion here, infimum of this portion here, infimum of this portion here, infimum of this portion, and it is getting increased successively. So here the infimum, if you collect terms of infimum values, it is a non-decreasing sequence converging to this. It converges to its values minus 1. So non-decreasing sequence, the infimum values, that is bounded above by minus 1. So it is converging. Any non-decreasing sequence is bounded above, is convergent to its LUB. So this is least upper bound for set of infimum values. So all the infimums are less than or equal to minus 1. So minus 1 is LUB value. So this is limit infimum value, and this is limit supremum value. The supremum values are greater than or equal to plus 1. So 1 is a GLB. So this is non-increasing sequence which is bounded below by 1. So that is converging to 1. So this is limit supremum, this is limit infimum. So this is a basic thing. So if you know this kind of basics, it's easy for you to understand the other idea. So that is the main theme of this lecture. That is, I'm not giving any new ideas to you, but whatever ideas that you have done so far is seen visually. I'm sure most of you could have not seen like this. Maybe some of you might have. Now, this is again, I told you the supremum values are the topmost portions and infimum values are the bottommost. So if you take this, so you could have seen this kind of graph in share market pricing or in some other things that you always see in the markets, in digital things. If you see this, even ECG readings goes this way. It's a zigzag way. So many wiggles up and down coming like this. But here, of course, the height of the wiggles gets decreasing, so it is probably getting converged because. So here you see the infimum values is getting converged to this number. It is coming down. Supremum values is coming down to a particular number. Infimum values going up to some number. So this number here, if you continue this pattern, they meet at some place. So supremum converges to some number. Infimum also converges to some number. If they converge to the same number, then the sequence is convergent. Whereas here the sequence is not convergent because supremum converges to 1, limit supremum is 1, limit infimum is -1, but they are different numbers. You see always a gap between them. If you see, a gap between them, then the terms of the sequence will not come closer to a particular number. So then this is not a Cauchy sequence. If it is not Cauchy sequence, it is not convergent, because I told you that with respect to sequence of real numbers, convergent sequences are Cauchy and Cauchy sequences are convergent. And therefore, if the limit supremum and infimum both exist, but if they are not equal like this, here limit supremum is +1 and limit infimum is -1, both exist but they are unequal, unfortunately. And therefore, though both exist, because they are unequal, naturally the limit does not exist. And you can also see a fact clearly, because the floor are less than the ceiling, the ground level is always less than or equal to the ceiling level, the roof level. Okay, in any room, the ground is the bottommost and roof is the topmost. Therefore, if limit infimum and limit supremum exist, then limit infimum will always be less than or equal to limit supremum, because this height can never go beyond this height, and this values cannot come below this value, because this is roof and this is floor. So that is the idea. So this is an example where supremum and infimum both exist but they are unequal. Okay, and this is an example for the supremum and infimum exist but they converge to the same number. In this case, supremum exists, infimum exists, they converge to the same number. Therefore, the sequence is convergent. Okay, this particular oscillation. So here you can see that supremum are aligned here. This is supremum and this is infimum. So these are also supremum, but limit supremum is the GLB of this, and limit infimum is the LUB of this. So limit supremum is this term, limit infimum is this term. Both exist, okay, but they are not equal. Therefore, this is also this collection of terms of the sequence which are zigzagged written here, resembling our initial chaotic sequence, is not convergent. Because for a convergent sequence, either the terms of the sequence should be very, very close to a particular number which you call as L, or the terms themselves should be very close to each other after a certain stage, making it a Cauchy sequence. If neither of these two conditions are satisfied, then it will not be convergent, as you can see here. Now we will consider the concepts of what is called limit of a real valued function. Now, real valued function is a function in which domain can be anything, any set, but the codomain is set of real numbers. Okay. So I'm going to consider f of x to be a real number for any x. Okay, that's what is meant by real valued function. Now, I take a point. You see, the concept of limit, continuity, and differentiability are discussed or defined even at a point. So if you say a function has a limit in the interval, say 0, 1, it means that it possesses limit at all points in that interval. If the given property becomes true for every point in the interval, then you say that property is true in the whole interval. But on the other hand, if it fails even at one point in the given interval, you discard it and say it is not continuous, it does not have limit in that particular interval. So for saying it doesn't possess that property, even one point, non-existence of one point is enough. But for saying that it holds that property in an interval, you have to check it for all possible points in the interval and give a more general proof. So basically, these are point-wise definitions. The concept of limit, continuity, differentiability are defined point-wise. So you can't say, if I say that the function possesses a limit at a point x is equal to 0, then I may not be sure enough that it possesses limit at x is 1 or 2 or something. So getting a limit at a given point may not guarantee the existence of limit even at the neighborhood point, like 0.5 or 0.2. You may not be sure about it. So you have to check one by one. Now, I'm going to take a point C here, and I'm going to choose a delta, which is so that I subtract from C to get C minus delta here and C plus delta here. So delta is a positive term, small number. So this is neighborhood of C, C minus delta to C plus delta. So what I'm going to do is, the limit definition says you give me an epsilon. There are 3 steps in defining a limit. You give me an epsilon. You probably give an epsilon to me. What I will do is, you also know about what is L. If I know that f of x tends to a limit L, then I know L. So this is that number L. This number L. I know L, the knowledge of L. What I have to do is, if you give me an epsilon, I will subtract epsilon from L and add epsilon to L. So I get L plus epsilon and L minus epsilon. This is some strip like which we saw before. So this is L minus epsilon. This is L plus epsilon. Now my aim, the third step is important. This is second step. The second step is L minus epsilon to L plus epsilon. So the next step is to choose. The second step is a crucial step. Find a delta for which the graph of the given function f of x will lie in that neighborhood of C. Between C minus delta to C plus delta, the whole portion of f of x will lie between L minus epsilon to L plus epsilon. So f of x is a distance of epsilon from L. Within this strip from L minus epsilon, it should not go beyond this strip from L minus epsilon to L plus epsilon. So this portion, you see, the whole portion of f of x is between L minus epsilon to L plus epsilon. So I have to choose such a delta. So the choice of deltas is by me. You give me an epsilon, I have to choose a delta for which between C minus delta to C plus delta, I should ensure that f of x is always a value between L minus epsilon to L plus epsilon. Because I know L, I know you give me an epsilon, I know what is L, you are giving me an epsilon. So I can easily find L minus epsilon and L plus epsilon. So I know these 2 lines. So what I should do is, I should find a delta in the second step, for which in the third step, my choice of delta should be such that the whole portion of f of x should lie between L minus epsilon to L plus epsilon. If I can do this for any epsilon that you give me, so for usually this delta depends on epsilon, because it's easy for me to choose the delta if epsilon is quite large, like 1 or 2. If the height is more, then it's easy for me to choose a delta, but the epsilon is quite small. The choice of delta is a little tricky, and you have to work it out. That is why you work delta and find delta in terms of epsilon in your class when you seek limit for a function at a point. Okay, so usually delta will depend on epsilon. Okay, I will come to this point later. Now we will see the concepts of limit, continuity of a function. Now see, these are some graph of a real valued function. Now this dotted here with bold mark here denote that it takes that value. So f of minus 2 is minus 1, whereas f of 3 is not 1 because there's a hole here. So this is a hole. So this portion here comes before 1 and after 1. F of 1, of course, is defined to be 4 here. F of 1 is dotted as 4. So f of 1 is 4. And f of 1 by 3 is a hole here. So it's that, but here it is minus 2. So f of 3 is 2. Listen, minus 2. F of 3 is minus 2. So this portion of the graph is just before 3. And after 3, I get this portion of the graph. So at the point 3, f is defined to be minus 2. And at the point 1, f is defined to be 4. At the point minus 2, f of x is minus 1. Now, when you try to compute the limit or something, See, the existence of limit is necessary for making a function to be continuous. Okay, so the first stage that you want to look is for continuity is to check whether the function possesses a limit. Only in the case when a function possesses a limit, you can talk about continuity. In fact, even basically, if you see, if a function is not even defined at a point, you can't probably think about continuity. So, for example, um, so here at the point -2, before -2, I don't have fixed value here. Before -2, the graph oscillates and there are so many wiggles here, coming down and going up, coming down and going up, so many oscillations that were taking place. So before -2, I do not know what is happening, but at the point -2, it is defined as -1. So if you actually try to compute the right hand limit, that is, right hand limit is computation of the values of f of x to the right side of -2. That is very close to -1. So f of x is to the right side of -2 is very close to -1. So that is why you get this continuation. And f of -2 is also -1. But if you take values of f before -2, it doesn't exist. So there's no f value, the function value, before -2. So the left hand limit does not exist, whereas right hand limit exists. In fact, right hand limit at -2 is equal to the function's value at the point -2. If that being the case, then the function is said to be right continuous, because you see there's no part here before this point, but at that point and after that the function is defined continuously. So this is right continuous. So the function f is right continuous at the point -2. So you get more problems in limit and continuity. So I thought of giving you about this information. Whereas at the point 1, if you see the left hand limit, f of 1 minus, if you take limit of f of x as x tends to 1 minus, it approaches to 3. You see, it's very clear. The graph of f, when you go before 1, it goes very, very close to 3. So limit of f of x as x goes to 1 minus, the left hand limit of f of x before 1 is 3, and after 1 is also 3. See, like if you take limit of f of x as x approaches to 1 plus, so it's coming very close to 1, but after 1. So when you take right hand limit, you take f of x values to the right side of the given point, and when you take left hand limit, you take values of f of x to the left side of the point. So if I compute limit of f of x as x tends to 1 minus, I have to take this portion. You see, this portion before this point 1 for f of x is very close to 3. So left hand limit of f at the point 1 is 3. Similarly, right hand limit here, this is also going to 3. So both left hand limit and right hand limit exist. They are 3, but unfortunately the function's value at the point 1 is not 3, it is 4. So because there's a gap here, there's a hole here, it is defined to be 4. So though both left hand limit and right hand limit are 3, the function's value at the point is defined to be 4. So it's not 3. Therefore, the portion of graph comes over here, it is not joining at this point. Therefore, there is a discontinuity here. And this type of discontinuity where both comes to the same height, but they are not joining here. That type of discontinuity is called removable discontinuity, because what I can do is I can plug this value, I can redefine this 4 to 3. I can bring this dot here and put here. If I bring this dot from 4 to 3, then it will join together. So then the discontinuity will be removed like this. So if this is defined by myself, so f of 1 is defined to be 4 by ourselves. So if to make this graph continuous at the point 1, what I can do is I can redefine f of 1 is 3. So if I define f of 1 is 3, then this dot will come here, and that will make the function continuous at the point 1. So that kind of, so if a point, it's called removable discontinuity. Both left hand limit and right hand limit exist, but they are equal to each other, but both value will not be equal to f of a, that particular function's value at the given point. In that case, what you can do is you can redefine f of a to the equal limit value. So if left hand limit and right hand limit converges to same number, then knowing that number, you can define f at that point to be the same number, which is equal to the left hand limit and right hand limit. In that case, the function will become continuous. So you can remove the discontinuity and make it continuous, and therefore such kind of discontinuities are called removable discontinuity. whereas this discontinuity cannot be removed. So this is remove discontinuity of first kind because the left hand limit does not exist. The limit even does not exist. There's no question of making it continuous. So it is only right continuous but not left continuous at the point x is equal to -2. Similarly, if you investigate the case for x is equal to +3 here, for left hand limit the function goes very close to 1. So f of x as x goes to 3 minus. If you take values of f before 3, very close to 3, but before 3, it is approaching to 1. But f of 3 is defined to be -2. And if you take f of x, limit of f of x as x tends to 3 plus, that means values of the limit of the function after 3, it is going to -3, as you can see. So the left hand limit of f at the point 3 is 1. It's very close to this value. Right hand limit is -3. So both left hand limit and right hand limit exist, but they are unequal. The left hand limit is +1. The right hand limit is -3. They are of different heights. Such type of discontinuity, so it's discontinuous naturally because before that it is here and after that it is here. So they are of different heights. So you can't join them. Like here I can join here because both, if the left hand limit and right hand limit are of same value, then I can join them by redefining. But here, unfortunately, the left hand limit and right hand limit both exist, but unfortunately they are not unequal. This is +1 and this is -3. So even if I redefine this to this number or this number, I can't do that. If I redefine this to be 1, then the function will be left continuous. If I redefine this to be -3, then it will be right continuous, but it will not be continuous in any way. So this kind of discontinuity where left hand limit and right hand limit both exist, but like here they are equal, but here they are unequal. If both limits exist but they are unequal like this, they're different heights, then such a discontinuity is called jump discontinuity. So this is an example of jump discontinuity. The left hand limit is +1, right hand limit is -3. Both exist, but they are of different heights. Therefore, at the point 3, you have a jump discontinuity. At the point 1, you have removal discontinuity. This is a discontinuity of first kind where you cannot make any way to make it continuous. So this is a discontinuity of first kind. Okay. One side limit does not exist. If both these limits does not exist, then it's called discontinuity of second kind or whatever it is. You can't make this continuous, but it is right continuous here. Okay, this is removable discontinuity. This is jump discontinuity. Okay, and at the point 5, before 5, the graph is approaching to 4, and after 5 also the graph is approaching to 4. At the point 5, the graph is exactly 4. So left hand limit is 4, right hand limit is 4. The function's value at the point is also 4. If everything coincides, then the function is continuous at that point. So f is continuous at the point 5. So this particular example, single example, conveys all types of things to you. Here it is right continuous, left hand limit does not exist. Here both limits exist, but they are equal, but it's not equal to the function's value at the point. So it's removable discontinuity. Here both limits exist, but they are unequal, so it is jump discontinuity. Even if you redefine this value to either this number or this number, it will either be left continuous or right continuous, but not both. But here it is continuous because both left hand limit and right hand limit exist. They are equal to the function's value at the given point. Here f of 5 is 4, as you can see. So it conveys a whole meaning. That's the main thing. Instead of doing as many problems, if you look at through pictures, it's very easy for you to understand. Maybe I can leave this exercise because of time to finish something. I can give some examples. You can see at the point 2, the function is left continuous because of the reason that I told you just now with the previous graph, the previous function here. You can probably understand the significance of this. So f of 2 is 1. At the point 2, the function is 1. And before that, if you take left hand limit at 2, it is converging to 1. So f of x is very close to 1, coming to 1. So the left hand limit of f of x is 1. F of 2 is also 1. But the right hand limit is approaching to -4. The f of x as x approaching to 2 plus. If you take the limit of f of x to the right side of 2, unfortunately it is not this number, it is some other number like -4. So it is left continuous. But because the left hand limit is equal to the function's value at that point, but unfortunately the right hand limit exists. Though it exists, it is not equal to this number. So it is left continuous graph. And if you see this example here, what kind of thing, you can take this as an assignment probably, but anyway, for the sake of completeness, I'm giving you. If you take this particular strip before 1, the left hand limit is this number. Function's value at the point 1 is 3. So f of 1 is 3 because there's a dot over here. There's a hole, it's not defined at that point. Okay. So f of 1 is 3. And if you take left hand limit of f of x very close to 1 to the left of 1, the graph is approaching to 3. So left hand limit of f of x is 3. F of 1 is also 3. So this is left continuous. Similarly, at the point 3, f of 3 is defined to be 1, and f of x to the right side of 3 is also approaching to 1. Therefore, this is continuous from the right but not from the left, because if we take values to the left side of 3, it is plus 2. This height is different from this number. Similarly, if you take to the right side of 1, you get 2. So left hand limit at 1 is 3, but right hand limit is 2. Therefore, this is different from this. So this function is left continuous at 1 as well as right continuous at 3, but not neither continuous at 1 nor 3, because a function is said to be continuous only if it is both left continuous as well as right continuous. In other words, only if I can join this and join this. Maybe if I draw a line segment like this here, joining these two values, then it will become continuous. But unfortunately, you have a separate strip here which is separating these two parts of the function. So it is neither continuous at 1 nor continuous at 3, but in fact it is left continuous at 1 and right continuous at 3. So these are some of the examples giving you all kind of understanding. You can immediately guess this case. It is left continuous at -4. Okay, because the right hand limit at -4 is a different number. It's -2, but from the left hand side you see it's approaching to this number, which is +3 here. So it is left continuous at here. At this point -1, f is continuous because the left hand side of -1 is going to +4. Right hand side is also going to +4, and f of -1 is +4. So it is continuous at the point -1. Both left hand limit and right hand limit exist. They are +4, and f of -1 is also +4. So it is continuous at the point -1. Whereas if we take the x value 2 here, the left side of f of x goes to -1. F of x approaches to -1 to the left side of 2. So left hand limit of f at the point x is equal to 2 is -1. F of 2 is also -1. So you see the left hand limit is equal to the function's value at the given point. But when you take the right hand limit, it is +5. You see, it is approaching to +5. So that is different from this value. So again, this is left continuous at the point 2. I leave this as an exercise to you. You can guess about this. Now, there are some important functions of significance which I go through quickly. If you take f of x is 1 by x, 1 by x is positive if x is positive and negative if x is negative. So this is a rectangular hyperbola. You can see xy is equal to c square. It's an equation of a rectangular hyperbola which you could have studied before. Here c square is 1. So y is equal to 1 by x basically represents a rectangular hyperbola which looks like this, in which the x-axis and y-axis are the asymptotes of the rectangular hyperbola. See, for rectangular hyperbola, the asymptotes will be perpendicular. In this case, the asymptotes are themselves the coordinate axis, namely x-axis and y-axis. Now, if you take x tends to +infinity or -infinity, then f of x goes to 0. F of x converges to 0. If you go to the left side, go as close as possible to -infinity, f of x will go to 0. Similarly, if you go to +infinity, we are as close as possible. If you extend this, f of x will go to 0. It will come very, very close to x-axis on either side of x-axis. But what will happen if you go very close to 0? If you go very close to 0, to the right side of 0 here, the value of f jumps to +infinity. So the right hand limit at 0 is +infinity, and left hand limit at 0 is -infinity. Okay, so at the point 0, the right hand limit is +infinity and left hand limit is -infinity. And I will come back to this function 1 by x little later, uh, somewhat later. And this function is a very important function called signum function. It's either mod x by x or x by mod x, whatever it is, because the reciprocal, this values, the function f of x is either +1 or -1. If x is positive, this is +1, and if x is negative, this is -1. And reciprocal of 1 as well as -1 is also the same numbers. 1 and -1 are self-reciprocals, and therefore I don't bother in writing x by mod x or mod x by x. It gives the same answer. So at the point 0, of course, it's not defined. So 0, because you get 0 by mod 0, which turns out to 0 by 0, and 0 by 0 is one of the indeterminate forms. So the function is not defined at 0, but after 0, you get, see, mod x is x if x is positive. So you get x by x when x is positive, which means 1. And mod x is -x if x is negative. So if x is negative, you can substitute this as -x. So you get x by -x, which is -1. So when x is positive, this is +1. If x is negative, this is -1. At the point 0, it's not defined. So you see, there is a jump discontinuity at 0, because the left hand limit at 0 is -1, right hand limit at 0 is +1. See, again, I want to emphasize a point that though the function is not defined at 0, I can talk about limit at 0, because when you talk about limit of a function at 0, I'm not considering or bothering about the function's value at the point 0, but I'm bothering about the function's behavior near that point, very close to that point. So when I talk about limit of f of x as x approaches to 0, what I'm basically concerned with is I'm going to consider f of x very close to 0, either to the left side of 0 or to the right side of 0, but I never will consider f of 0. I am not at all concerned with f of 0. What is function at the point 0? That I am not basically concerned with at all. So in general, when you talk about limit of f of x as x approaches to a, you want to find f of x very close to a, but not at the point a. You have to remember the computation of limit is not at the point, but very close to that point, in the neighborhood of that point. In case if that limit value happens to be equal to the function's value at that point, then the function becomes continuous. That is that is the meaning of saying limit of f of x is f of a as x approaches to a. F of x tends to f of a as x approaches to a, which means if the behavior of the function near to the point is exactly same as the behavior of the function at the point, then the function is said to be continuous, and that is what is depicted here. So if the behavior of the function near to -1, namely this height and this height, is exactly same as the given value at the function's value at that point, then the function will be continuous. It means if I know that f of -1 is 4 here, you see. So I know that f of -1 is 4. If the behavior of f before -1 goes to 4 and after -1 is also going to 4, if the behavior of the function before that point and after that point is also equal to the function's value at that point, then the function will be continuous. This is what we mean to say f of x approaches to f of a whenever x approaches to a. Okay, that is the basic meaning of. So when I talk about limit, I'm not bothered about whether f is defined at that point. I'm basically bothered about how f behaves before and after that point. So in this case, the right hand limit, because when x is positive, the function signum function is always 1. The right hand limit at 0 is 1, left hand limit is 0. So as I told you, both limits exist, but they are unequal. As you can see, here we saw that in this example, both limit exist, but they are unequal. In this case, we call such a discontinuity a jump discontinuity. So f is not continuous at x is 0, because 0 is a point of jump discontinuity. In fact, 0 is not even defined for this. It's not in the domain of this function. Okay. Now, for 1 by x square, instead of 1 by x, if we take 1 by x square, even if x is negative, x square will become positive. So the graph of 1 by x square is above x-axis, and x approaches to plus infinity or minus infinity, it approaches to 0. Whereas if x approaches to 0, both right hand limit will go to plus infinity as well as left hand limit is also going to plus infinity. Unlike 1 by x. For 1 by x, if you go before 0, the value jumps to minus infinity. Whereas if you go after 0, it goes to plus infinity. So right hand limit is plus infinity and left hand limit is minus infinity. See, if the value goes near to plus infinity and minus infinity, you don't call that as a limit. You say limit does not exist. Okay. So here we don't have limit at 0 because right hand limit is plus infinity here and left hand limit is minus infinity, which are not real numbers. Remember, minus infinity plus infinity are not at all real numbers in proper real number system. Okay. Now, if you take this particular function, here again limit does not exist at x is equal to 0 because the right hand limit is plus infinity, left hand limit is also plus infinity. So there's a big small difference. Though the limit does not exist for both the functions, here the both sided limits are plus infinity, but whereas for 1 by x, left hand limit is minus infinity and right hand limit is plus infinity. Now, if you take sine 1 by x or sine pi by x or something like that, and if you see the value of limit of f of x, this function at x is equal near to 0, unfortunately there are so many wiggles at close to 0, you can't decide which is closer, which is farther. I mean, you can't possibly guess whether f of x is close to L or away from L, because there are so many wiggles and so many oscillations near 0. It is very tightly packed. There are infinite number of wiggles at the point 0, near to this point 0. So as it is, I can say limit of sine pi by x or sine 1 by x, rather, whatever it is, you can rescale this number pi to 1. So limit of sine 1 by x or limit of sine pi by x at x is equal to 0, because near that point 0 there are so many wiggles, so limit does not exist. So if you have a function in which there are infinitely many wiggles near the given point or in the neighborhood of the given point, then limit does not exist. Now this is a very famous example, sin x by x. So left hand limit at the point 0 is approaching to 1. Right hand limit is also 1. But at the point 1, at the point 0, you get sine 0 by 0, which is again 0 by 0, as we saw in signum function. So it is not defined at the point 0 by 0. But what happened here is, in the signum function, right hand limit is 1, left hand limit is minus 1. They both exist, but they are unequal. So it is jump discontinuity. Whereas for this function, sin x by x, the fortunate thing is, though the function as it is not defined at 0, both left hand limit and right hand limit are approaching to the same height, unless in signum function they approach to different height, 1 and minus 1. For sin x by x, they approach to the same number, 1. But unfortunately, the function is not defined at x is equal to 0. So before 1 and after 1, they approach the same height. So if I define f of 0 as 1, I can remove this discontinuity and make it continuous by properly defined. So if I define, say for example, f of x is sin x by x if x is not equal to 0, and f of 0 is 1. If I define f of x as 1 and x is equal to 0, then I will make this function continuous. So this is an example of removable discontinuity. Now here again at the point, this is graph of this function x square plus x minus 6 by x square minus x minus 2. You can actually factorize these two quadratic terms and cancel out x minus 2, and you can see the limit of x tends to 2 as such. You see limit of x tends to 2. You see there is this graph approaches to 5 by 3. This is 5 by 3 value, because if you cancel x minus 2, you get, if you put 2 here, you get 2 plus 3 is 5, you get 2 plus 1 is 3, so you get 5 by 3. And that is actually, that is not actual computation of limit. See, before 2 and after 2, this is computation of left hand limit. You start at 1.5 and go very close to 2 to the left side of 2, up to say 1.999. This is number which is very close to 2 but less than 2. And you see that f of x is approaching to the number 1.6666 something, which is 5 by 3. If you divide 5 by 3, you get this number 1.6, infinitely repeating. After decimal point, 6 gets repeated infinitely often. That is what you get upon dividing 5 by 3. Okay. So, and at the point near to 1, if you see near to 1, it doesn't exist. The right hand limit is plus infinity, left hand limit is minus infinity, just like 1 by x. Okay. So this is the basic idea behind all this computations. So the actual calculation of limit is this. See, when you compute limit x tends to 2 of f of x, you plug in values very close to 2, before 2 and after 2, and you see whether they have come to the same number. Here it is coming to the same number. Okay, namely 5 by 3. But f at the point 2 is not defined because 2 is common factor to the numerator as well as to the denominator. So f of 2 is not defined here. Now let me give you examples of functions which are floor functions and ceiling function. Floor function is a for a function for a real number. See, for if x is a real number, then floor of x is defined as the greatest real integer for which that is less than or equal to the given number. Otherwise, you have to collect all the numbers less than this given number, less than or equal to this number, and pick the greatest among them. Similarly, the ceiling function is something like you pick all the numbers greater than the given number and pick the least among them. So this are called floor and ceiling because for any number, real number, the ceiling function will be in the right hand side, and this is like topmost and this is bottommost. Whereas if you take two integer 2, if the input value itself is an integer, then floor function and ceiling function will be same. Okay, they are both same. But if you take any non-integer, then floor function will be 1 less than the ceiling function. For any non-integer, floor value is 1 less than the ceiling value. So for example, ceiling of and floor of the value pi, when x is pi, floor value is 3 because pi is 3.14 approximately. The floor value of pi is 3 and ceiling value is 4. For any non-integer, the floor value is always 1 less than the ceiling value. Keeping this in mind, we have drawn this. You can see at the point -1, the ceiling value, the floor value is -1. It comes up to this, but at the point 0, it is 0. So it remains 0 up to 1. At the point 1, it is 1. So it is just like what is called a step function. See, the beautiful thing about this floor function and ceiling function is similarly constructed, but only thing is the portion from -2 to -1 is from -1 to 0 here. The portion from 0 to 1 is from 1 to 2 because this values I told you for non-integers are 1 more than the floor values. The values of ceiling are usually 1 more than the floor value. So this jumps to here, this jumps to here, this jumps to here. So this values here are 1 more than this. So for example, from 1 to 1.5, you have this here. From 1 to 1.5. From -2 to -1. So from -1 to 0 here. See, this is from 0 to 1. From 0 to 1 in the floor function, you get 0. Whereas from 0 to 1 in the ceiling function, you get 1. So this values are 1 more than this. But anyway, it looks similar. If you look in a grand scale, both are resembling what is called a step function. But the basic difference between ceiling being 1 more than the floor is this is left continuous at all integer points, and this is right continuous at all integer points. So the ceiling functions are right continuous, whereas the floor functions are left continuous. And you can also see these two functions are examples of functions which have countably many discontinuities. That is, both of these functions are discontinuous at any integer point. So for example, at -1, I have right hand limit -1, but left hand limit drops down to -2. So the function is not continuous at any integer point. It is continuous until you get an integer, you reach an integer. When you reach integer, you jump 1 to the next value. You go to the same value, remain at the same value until you reach the next integer. Whenever you reach the next integer, you jump them. So you see this kind of step functions are not continuous at any integer point. In particular, the floor function is left continuous and ceiling function is right continuous, and both have infinitely many discontinuities, and the discontinuities occur at every integer point. So these are examples of functions which have countably many discontinuities because integers are countable. Okay. Now I will probably give a theorem, compute the limit by using a theorem called squeeze theorem, or some may call this a sandwich theorem, or whatever. There are several names for that. So there are some other names which I can't remember, but usual terms are squeeze theorem or the sandwich theorem. So you see the green color portion is graph of x sine 1 by x. Okay, this is x into, we saw sine 1 by x graph here, which has infinitely many wiggles. But if you take x sine 1 by x, the limit of sine 1 by x does not exist because near 0 there are infinitely many wiggles, so it does not exist. But if you consider x into sine 1 by x, you see the near 0, the values are going very close to 0. It approaches to 0. So what happens is, to compute the limit of x sine 1 by x, you have this wonderful idea. The whole portion of x sine 1 by x, which is the green portion graph, the graph of x sine 1 by x, lies between plus mod x and minus mod x. See, the blue graph is minus mod x. So the lower bound for this function, x sine 1 by x, is minus mod x, the blue graph, and the red graph is plus mod x. So you can write down an inequality like minus mod x less than or equal to x sine 1 by x less than or equal to plus mod x. That means this values x sine 1 by x is squeezed between minus mod x to plus mod x. Now if you compute the limit as x tends to 0, both this minus mod x and plus mod x meet at 0. Both of this function minus mod x and plus mod x will be 0 at x is equal to 0. So if you try to compute this limit at as x tends to 0, this is between two values which goes to 0. Therefore, this also goes to 0, which means that limit of x sine 1 by x as x approaches to 0 is also 0. So this limit exists. In fact, the limit value is 0 because it is squeezed between two values, namely minus mod x and plus mod x, which goes to 0 as x approaches to 0. So this is a very interesting application. Squeeze theorem is a very fascinating theorem. Some may call sandwich because when you make sandwich, you put two breads, one above and one below, and put some materials behind it, in between them, and you make it in such a way that it's stuffed between this main stuff with vegetables and other things, or get stuffed between the upper bread portion and lower bread portion. This is upper bread portion, mod x. This is the lower bread portion, minus mod x. So I know that it is going to get near to lunchtime, maybe very close to lunchtime. So it's very apt that I'm saying sandwich theorem. So wait till a few more minutes, I will finish and go. Then you can have a good lunch. Now, I'm going to find limit of x squared sine 1 by x rather than x sine 1 by x. So blue graph is graph of x squared sine 1 by x. Again, you see the upper limit here. Now the upper bread portion is x squared. So it is bounded between minus x squared and plus x squared. I can squeeze this function x squared into sine 1 by x between minus x squared to plus x squared. Minus x squared is below this function, and as you can see from the graph, and plus x squared is above this function. So in fact, x squared sine 1 by x is squeezed between minus x squared and plus x squared. So as x approaches to 0, when x is very close to 0, see what happened. This goes to 0 when x is 0. This goes to 0 when x is 0. Because this is between these two values, which is going to 0 when x approaches to 0, it follows that this also go to 0, as you can see here. So x squared sine 1 by x has limit 0 when x approaches to 0, because it is squeezed in between two quantities which goes to same number 0. So this is one of the beautiful application of squeeze theorem. It's quite difficult to compute the limit of this through other ways, like you can compute left hand limit, right hand limit, and do some other calculations. You can get the same answer. That's not a big issue, but this method is quite elegant, visually very appealing to see why that happens. Okay. Now this is the graph of sine 1 by x. This green graph here, not green. I think it's green graph. This is graph of sine 1 by x. Okay, sine x by x, not sine by x. I'm sorry, I have not written the function here, so that's what makes me confusing. This is sine x by x, this graph, and that is squeezed between 1 by x. So this green graph, one comes above here and one comes below here in the first quadrant and third quadrant. So this is 1 by x and this is minus 1 by x. This red graph is minus 1 by x. So the whole portion of sine x by x is squeezed between minus 1 by x and plus 1 by x. In fact, you can see that minus 1 by x, sine x by x is always a value between these two numbers. When x is less than 0, you see 1 by x is less than or equal to sine x by x, that is less than or equal to minus 1 by x. If x is greater than or equal to 0, then minus 1 by x is less than or equal to sine x by x, that is less than or equal to plus 1 by x. So, but the upper bound and lower bound will change before and after 0. Before 0, the lower bound is plus 1 by x for sin x by x, and upper bound is minus 1 by x. But after 0, when x is positive, the lower bound is minus 1 by x and upper bound is plus 1 by x. But anyway, the function, the whole part of the function sin x by x is squeezed between minus 1 by x and plus 1 by x on either side of origin. But what is interesting here is when x tends to plus infinity, you see both plus 1 by x and minus 1 by x goes to 0. Therefore, limit of x tends to 0 sin x by x as x tends to infinity is 0. So we saw before the limit of sin x by x as x approaches to 0 is 1. You can get that through removable discontinuity part, because both left hand limit and right hand limit at 0 is 1. So you can define this point to be 1, redefine that to make it continuous. But limit of sin x by x approaches to plus infinity is 0, because when x is near to plus infinity, it is bounded above by 1 by x as well as by below by minus 1 by x, which goes to 0. They are very close to x axis whose value is 0, y is 0 here. So this portion sin x by x is squeezed between plus 1 minus 1 by x and plus 1 by x, both going to 0 as x approaching to infinity. Therefore, sin x by x has limit 0 when x approaching to plus infinity. The same thing happens to the minus infinity. Only thing is the role of upper bound and lower bound gets interchanged, but the same conclusion is what you have. So from this graph, I can conclude the limit of sin x by x, whether x approaches to plus infinity or minus infinity, in both cases it is 0. Okay. Now let me come to continuity of function. In fact, this is composition of continuity of function. So I told about continuity. The behavior of function near the point, that is limit value, is equal to the function's value at the given point, and the function is said to be continuous. I mean, practically speaking, loosely speaking rather, vaguely speaking, if you can draw up the portion of the graph near the given point without lifting your pen or pencil from the paper, the function is said to be continuous. That's very easier way of seeing continuity. Now the red portion here is portion corresponding to x square graph. This is floor of x square. So the green portion, you see the floor of x square. This is sine of x square, blue portion. So this is composition of function. I have a function here, floor of x square. Floor function is a function, as you have seen, this is a function. Sine of x square is another function. So this is composition of function. So if I take f of x as x square and g of x is sine x, then this is g composition f. Okay. Similarly here, this is composition of two functions. You know that if f is continuous and g is continuous, then composition of continuous functions is continuous. So this is a visual example of that. F is x square, that is continuous, as you can see from the red graph. Sin x is also continuous, as you know, it's an oscillating graph. So the best example for bounded function is both sin x and cos x. It always, both sine and cosine will always lie between two numbers, minus 1 and plus 1. They can't exceed between these two values. I mean, sin x can't be greater than 1 or less than minus 1. If sine can't exceed this number, cosine also can't exceed this number, because cosine are derived values of sine. See, the value of cos is actually written as cosine. So whatever sine takes, similar values is what cos will take. In other words, the range of cos is same as range of sine. In fact, the cos values are obtained from sine value. That is why we write cosine. Okay. So this is continuous, this is continuous. So composition of two continuous function, as you see, is continuous. So the blue graph is continuous. Okay, because sine is continuous, x square is continuous. So if in exam, in net exam, if you are asked to find which among the following are continuous, the options are given like sine x square, something like that, cos of 3x square, something like that. You know that 3x square is continuous, cos is continuous, and composition of continuous functions are continuous. So using this particular fact, you can immediately guess and conclude that cos of 3x square is continuous, as well as sine of x square is continuous. As far as you know that these two constituent functions are continuous, their composition is also continuous. Okay. So for example, if x is greater than 0, I can immediately tell that sine of log x is continuous. There's no need to think beyond that, because when x is positive, log x is continuous, sin x is also continuous. So sine of log x is composition of sin x and log x when x is positive, and therefore that is going to be continuous. So you can probably guess like this and conclude your answer immediately within no time. So the theorems convey this message. That is what I'm going to probably my aim in this lecture, okay, this session. Floor of x square, you know, the problem comes here. Floor of x square is something like green graph which gets discontinuous. See, small portion here, small portion here, small portion. It is clearly discontinuous. It is not continuous. Small portion, it will look like a step function. So the green graph behaves like a step function with smaller broken segments, okay, either to the left side and to the as well as to the right side of origin. The reason is because floor function is not continuous. I know that floor function has infinitely many discontinuities at every integer point, and therefore you see that behavior here. At every integer point, say for example, 1 is between 0 and 2. At 1, it get discontinued. At 2, it is getting discontinuous. At 3, it is getting so at every integer point, because the floor function, so if you take any value of x for which this happens to be an integer, so this graph, green graph, is discontinuous at all points wherever x square is an integer, because I know the floor function is discontinuous at all integer points. So for example, this floor of x square is discontinuous at x is root 2, because root 2 square is 2 and floor of 2 is 2, and that is discontinuous at that point. So if you take root 2, which is greater than 1 somewhere here, this is root 2 here, so that is discontinuous, okay. So at 1 it is discontinuous because floor of 1 square is 1, that is 1. At 2 it is discontinuous because 2 square is 4. So whenever you choose x for which x square is also an integer, then floor of x square will become discontinuous. Okay. So here composition of continuous function x square is using another function which is not unfortunately continuous makes it discontinuous. In fact, the points of discontinuity are precisely the points where this function is not discontinuous. I know that floor of any function is not continuous at every integer point. So floor of x square will not be continuous at points where x square is an integer. At all other points, whenever x square is not an integer, it is continuous. So that is why it is having some broken segments here. This portion is continuous, but whenever x square happens to be an integer, it gets broken. You see the graph here. And now coming to differentiability, see, the idea of differentiability is somewhere is very important, because see, when you talk about the concepts of functions, the basic idea of a function that, can have as a limit. Then the second stronger condition is limit. The third stronger condition is differentiability. In other words, if I know that a function is differentiable at a point, it will be continuous at that point. And if a function is continuous at a point, it will have a limit at that point, but not conversely. If a function possesses a limit at a point, it may not be continuous at that point. The classic example is sine 1 by x. The limit as x tends to 0 of sine x by x is 1, because both left hand limit and right hand limit is 1, but it is not continuous because there is a hole here. In fact, the function is not defined even at x is 0. When the function is not even defined at a point, it will not be continuous. You will get a gap or hole at that point. So though the limit exists, it is not continuous. So existence of stronger condition naturally implies existence of weaker condition, but not the other way. The existence of weaker condition need not imply the existence of stronger condition. And a function may be continuous but may not be differentiable. And the example is this. See, this is x here. This is function of graph of x. This is mod x. See, the graph of mod of some function will be like this. Whenever a function is positive, it will retain the same value. Wherever function is negative, you have to just reflect it. So the mod x is obtained from x by the way that whenever x is positive, in mod x, mod of that value. So mod x is modulus of x. Okay, so this is x. If you take beyond after x value after 0, this is positive, so it remains in the mod x also. It remains as it is. There's no change here. But before 0, the values of x is negative. So in mod, if you take mod of negative values, it becomes positive. So what you have to do is just reflect, just like mirror image. If it is bottom, it comes to top. So if I take reflection of this, treating this as a mirror, x-axis as a mirror, this gets reflected here, just like this. So that is graph of mod x. And you see, mod x is not differentiable, though it is continuous. See, it is continuous. It is clearly there's no gap here. So it is continuous at x is equal to 0, but not differentiable at that point. In general, I can give a common idea to you. Those students who are interested can note it down. Wherever f of x is continuous, mod f of x, wherever f of x is differentiable, leave away f of x. If f of x is known to be differentiable, then mod f of x will not be differentiable at the points where f of x becomes 0. So if I know that f of x is differentiable, then mod of f of x is not differentiable at the points wherever f of x is 0. So this is graph of x. X becomes 0 if x is 0. Therefore, mod x will not be differentiable because x becomes 0 at 0. Okay. So I'll give some more example. So x square minus x minus 2. This is a parabola graph, second degree polynomial. So you see f of minus 1 is 0, f of 2 is 0. If you put minus 1 here, you get 0. And if you put plus 2 here, you get 0. So f of minus 1 is 0, f of plus 2 is 0. So if you take modulus of this function, so before minus 1 it is already positive, so that will remain as it is. And after 2 also the function is positive, so that will remain as it is. But between minus 1 and plus 2 the graph is negative. Therefore that will become mirror image. So the mirror image of this portion will be like this. So that is reflected here. So if this is f of x, this is modulus of f of x, which I call as g of x. Okay. So this is modulus of this, and you can see f of x is clearly continuous as well as differentiable at all points. See, the existence of differentiability guarantees the existence of tangent drawn that can be drawn at the given point. So if you say a function is differentiable, that means geometrically, as per the Leibniz idea, that you can always draw a tangent to the function at the given point. So you get existence of tangent to the point. In fact, in fluid mechanics, differentiability guarantees the smoothness of the fluid. The function is known to be characterizing fluid motion is known to be differentiable, then you can conclude that the fluid motion is smooth. So the idea of smoothness in applications is guaranteed by getting this differentiability condition. The function wherever have sharp edges will not be differentiable. You can see f of x will become 0 at the points minus 1 and 2. Therefore, modulus of this will not be differentiable at the points where f of x is 0. So this function will be differentiable at all points except at 2 points where those 2 points are zeros of f of x. That is, you compute the values of x for which this becomes 0, the roots of f of x. So I know that I just told you that minus 1 is where f of x becomes 0, f of minus 1 is 0, f of plus 2 is also 0, because those are the points where the graph meets x-axis. Geometrically, the roots of a function are values of x for which the graph meets x-axis. So the function f of x becomes 0 at minus 1 and 2. Therefore, those are the 2 points where for which modulus of this term is not differentiable. So though this is differentiable at all points, this is not differentiable at 2 points because those 2 points are precisely the points where f of x becomes 0. In general, modulus of f of x will not be differentiable wherever f of x becomes 0. Okay. So for example, sin x is a continuous function, differentiable function, but mod of sin x is not differentiable wherever sin x becomes 0. And you know that sin x becomes 0 when x is 0, when x is pi, when x is any integer multiple of pi, whenever x is n pi, when n is an integer. So mod sin x will not be differentiable at any integer multiple of pi. So, and you know that sum of two differentiable functions is differentiable. And this is an example of a function, the green graph here. This is graph of x plus mod x. X plus mod x. I'm not going to give the explanation for this. You can easily see how this graph has come. Mod x is plus x when x is positive. So whenever x is positive, this is x plus x 2x. So this is when x is positive, this is 2x. Okay. When x is negative, mod x is minus x. So x minus x is 0. So you get 0 here. Similar explanation will give this value. Whenever x is negative, mod x is minus x. So this is x minus minus x, that is plus 2x. So this is 2x, the graph of 2x. This is 2x when x is positive for green graph. This is continuation of 2x. This is 2x graph. Whenever x is positive, mod x is plus x, so x minus x is 0. So the violet portion graph will correspond to G and this is F. Because mod x is not differentiable at x is 0, as we saw here, the slope of this is -1, left hand derivative is -1, right hand derivative is +1. They both exist, but they are not equal to 0. Because I told you the basic idea that x becomes 0 at the point 0, and so mod x is not differentiable at 0. So mod x is not differentiable at 0, so f is not differentiable at 0 because there's a sharp turn here. Wherever the function gets sharp turn at a point, it is not differentiable at those points. Okay, so f is not differentiable at x is 0, g is not differentiable at x is 0. But what is f plus g here? You see when you compute f plus g, this plus mod x and minus mod x will cancel. You get 2x. 2x is a straight line segment that will become continuous. So there's a possibility of two non-differentiable functions for which still their sum becomes differentiable. Okay. Same thing applies for continuity also. You may give examples of two discontinuous functions whose sum may be continuous. This is another curious question. There's an example of a function where one is continuous, the other one is differentiable, the other one is non-differentiable because mod x is not differentiable at x is 0, whereas x is differentiable for all x because it's a straight line segment, and mod x is not differentiable at x is 0, but this product, namely x into mod x, is differentiable for all x. So this is product of one differentiable function, another non-differentiable function, but still the product may become differentiable. So x into mod x is differentiable at x is equal to 0. See, the graph is not having sharp turn at 0. It is very smooth here. Whenever a graph is smooth at the given neighborhood of a given point, then it is differentiable at that point. It's easy to see. In fact, when x is greater than or equal to 0, it is plus x square. When x is less than or equal to 0, it is minus x square. Okay, it's really differentiable at x is equal to 0. So there's a sharp turn at -1 here, so the function is not differentiable at -1. There's a sharp turn at 2, so the function is not differentiable at 2. Except these 2 points, it is differentiable at all points. Okay. In fact, if you compute the differentiability, you get this answer. So I told you the slope of this line is -1. The slope of this line is 2/3, and slope of this line is -2. So that comes here. So the function, this is derivative picture of f dash, the derivative of x. So as you see, but even I do not have to know these answers. Whenever a function have sharp turns or sharp edges somewhere, so sharp vertices, at those points, the values of x which have sharp turns are the points for which f is not differentiable. This is easy way to guess where the function is not differentiable. At -1, f is not differentiable. At 2, f is not differentiable because of this reason. Okay, and then probably the function is said to be uniformly continuous in a common way, that if you take any delta, if you take a rectangle of length say 2 delta, the whole portion, if you take a rectangle whose length is 2 delta and breadth is 2 epsilon for given epsilon, the whole portion of the graph lies inside, between this length and this breadth, the whole portion of the graph lies inside that rectangle, wherever the same delta, the same length here. So I have given many rectangles here with same length and same breadth, and you can see wherever you take the graph, the whole portion of the graph lies inside the rectangle. If that being the case, then the function is said to be uniformly continuous. Whereas in this case, you see, for this delta epsilon, the whole portion of the graph is inside this rectangle. Here also it's inside, but if you take this portion, after this part, it is going outside the rectangle. You see, this is 2 delta. So at this point, I have not completed the rectangle. There are some portion here, but if you take this portion here, the graph of the function goes beyond this rectangle, outside the rectangle. So though it is continuous, it is not uniformly continuous because the portion of the graph goes beyond that rectangle. So these are some visual representations. So if you take 1/x, this is a classical example even in Tom Apostol book, showing that 1/x is a continuous function when x is greater than 0. It's uniformly continuous whenever x is greater than 1, and in the intervals from 0 to 1, open interval 0 to 1, it is not uniformly continuous 1/x. The reason is because of this. So this is my delta, this is my epsilon. You see, up to this width, the graph of the portion goes beyond this rectangle. எனக்கு இது வரைக்கும் வரணும் எனக்கு, பட் இங்கேயே வெளியில போயிடுச்சு கிராஃப். In the whole portion of this width, if you see, this portion is not covered here, this portion is not covered here. Even before completing the length, the graph goes up, away from the rectangle. It's going below and as well as above. So the function 1 by x is not uniformly continuous, whereas the root x, the whole portion of root x is inside the rectangle, so it is uniformly continuous when x is positive. Whereas if we take 1 by x graph after 1, say 2 or more than 2 like this, then the whole portion of 1 by x is inside the rectangle as well as root x. Therefore, 1 by x is uniformly continuous when x is greater than 1. But whenever x is close to 0, it is not uniformly continuous, in the neighborhood of 0. So this is the graph of sin x, you see, graph of sin x. And for this same width here, this is epsilon, 2 epsilon, this is 2 delta, which I have chosen conveniently. You see the whole portion of sin x is always inside this rectangle. It never comes outside the rectangle. For this portion, it always lies inside this rectangle. For this portion of sin x is always inside the rectangle. So this is uniformly continuous. Similarly, cos x is also uniformly continuous. Whereas if you take this x square graph, this is x square, you see for x square, whenever x is very close to 0, if you take delta width, the whole portion of, see, if I take this rectangle from this to this, for this particular width, the whole portion of x square is inside the rectangle. Similarly, for this delta, the whole portion of x square is inside the rectangle. So x square is uniformly continuous at the point x is equal to 0, because the whole portion of x square for a fixed value of delta, the same delta, makes f of x lying inside the whole rectangle. Whereas if you go beyond some values like greater than 0.5 or very close to 1, and if you take same delta rectangle with same delta value here, very close to 1, if I'm taking it near to 1, then what happens is, see, up to this portion, the graph of x square lies inside the rectangle. But if you take this portion, it's coming out. If you look at clearly, so that is marked in red color here. Okay. So up to this green portion, this portion, the graph of x square lies inside the rectangle. But when you take this portion, it is coming down, and when you take this portion, it is going above. So the graph of x square is not completely inside this whole rectangle. If before this, up to this portion, it's coming down, so it is below the rectangle, and for this portion, it is above the rectangle. Like the whole portion of x square is not completely lying inside the whole rectangle. Like here, it is not so. The part of x square is missing out, and when x is large, whole portion of the missing part will be large, and the portion of x square inside the rectangle will become smaller and smaller, which means to say that x square, though it is continuous, it is not uniformly continuous whenever x is large. In fact, it's easy to show that x square is continuous near x is equal to 0 like this, whereas if x is 1 or more than 1, it is not uniformly continuous, though it is continuous, because when you try to plot them in the graph, the portion of x square will go away from the rectangle, okay, near the given point. And same thing happens for the graph e to the power of x. See, whenever x is less than 0, for same width of delta, the whole portion of e power x lies inside the rectangle, which means that e power x is uniformly continuous for all x less than or equal to 0. But whenever x is positive, unfortunately, this width portion is here, but e power x increases rapidly when x is large. Therefore, if I take x quite larger number, the portion of e power x goes outside the rectangle. Here it is above this rectangle and below this rectangle. So there's missing out here, missing out here. So which means that though e power x is a continuous function for all x, for any real number, it is uniformly continuous whenever x is less than or equal to 0. But when x is greater than 0, it is not so. Though it is continuous, it is not uniformly continuous. And then I took some examples of function of several variables. Z is f of x y is x square y square by 3x power 4 plus y power 4. If you look at, compute the limit of this function as x goes to 0 very closely. So what I can do is, if I can go through x-axis, I can go through y-axis, I can come through any axis. But you see different heights here. This height is different from this side. This peak is different. So near to 0, you get different values, peak values, which means you get different limit values when you approach that value. So this doesn't have a limit as x tends to 0. If a function doesn't have a limit, it's not continuous at that point. So as it is not continuous. Okay. You can very well see when you go near along the line x is equal to 0, this will become 0. When you go along the line y is equal to 0, this will again go near to, it will become 0. So when you travel along y axis or x axis, it is going to 0. But when you travel along y is equal to x, like this, which is a straight line, it is coming to some value. Like if you put y is equal to x here, you get x power 4 by 3 x power 4 plus x power 4. So you get x power 4 by 4 x power 4, this 1 by 4. This is the peak value, 1 by 4. If you travel through minus x, if you travel through this value, if you travel this value, they are of different height. This height is smaller, this height is larger, this is 1 by 4. This height, they are not equal to 0. So depending upon different directions of approach, you get different height values. Therefore, the limit does not exist. It's an easy way to see. The same thing happens here. You see different peaks values here. One is very large here near 0, one is somewhat smaller. So the limit does not exist. I'm going, and this function is a very nicely behaving function. It is continuous at the 0. You see below 0 it is like this, and above 0 it is very smooth function. At the point 0, the limit is 0. Okay. So any direction if you approach, it is going to 0 here. Whatever direction you choose is going to 0. In fact, this is continuous function at the point 0. And this is the directional derivative. So for a surface that is defined like this, what you can do is you choose the direction. This is direction of the vector v, this is direction of the vector u. So what I can do is take this curve in the direction of v and take this curve in the direction of u and differentiate that curve, because for a given plane curve I can know how to differentiate it. So this is directional derivative. So if I take this particular curve and differentiate it, that is directional derivative in the direction of u. And if I take this particular curve, just peel it, if you cut this part and find differentiate that particular curve, that is directional derivative at the function in the direction of v. So this curve is plotted here. So you cut the surface at that point, you take the boundary here. So this, and if this is a curve here, this edge. So if you find the derivative of this function at some point here, this point I say x naught, this is the derivative in the direction of v. So this is directional derivative in the v, and this direction. Now a function is said to have a directional is said to be differentiable if its derivative value in any given direction is going to be same. Supposing if the derivative at u is different from derivative in the v, though in each direction you get some value, it is not differentiable. If the derivative values at each direction gives different values, then the function will not be differentiable. It is said to be differentiable, the function of several variable, only if the derivatives at along each of the direction that you compute is going to be identical. And partial derivatives are special case of directional derivatives. You see, this is the surface. I just cut this point. I want to find the partial derivatives. So in fact, if you take the direction of u as x-axis and direction of v as y-axis, if you take u as x-axis and then take the directional derivative along x-axis is partial derivative of f with respect to x. The directional derivative along y-axis, if you take v as y-axis, this is partial derivative of f with respect to y, that is dou f by dou y. In fact, for this particular function, to find the directional derivative along x, I fix y is constant, put x is equal to b, put y is constant, so you get this particular curve. That curve is here. If you find slope of that, you get 1. So dou f by dou x at the point origin is a straight line resembling here y is equal to x, whose slope is 1. So this is how the idea of partial derivatives are observed. In fact, partial derivatives are special cases of directional derivative in which directions are chosen to be along the coordinate axis. But directional derivatives are more general. So I think with this I can wind up. I don't take much more time than this. I thank our HOD, Professor R. Venkatramanan, for giving this wonderful opportunity to share what little I know with you. I hope this session will be useful to you, and if possible, we'll meet again. And I'll do more interesting exercise in the upcoming classes. Thank you.
On behalf of PG and Research Department of Mathematics, DG Vaishnav College. Thank you, sir, for spending your valuable time in our C4 session. Really, it's a wonderful session to all our students, research scholar, and CSIR aspirants. I would like to thank Professor R. Venkatramanan, Head PG and Research Department of Mathematics, for organizing this C4 workshop. I am very proud to inform about our next webinar titled Exploration in Number Theory. Resource person Dr. R. Sivaraman, Associate Professor, Department of Mathematics, DG Vaishnav College, Chennai, will be held on 6th February at 10:30 a.m. Our next C4 session will be held on 6th February at 6 p.m. Thank you.